let's 2 weeks ago we talked about such kind of linearity error definition. For integral nonlinearity, actually I forgot to tell you why we have such kind of definition, integral or differential. Integral, I mean in calculus, it looks like this, right? But by definition, actually that is summation, but the difference should be very small. Okay, and again, yeah, differential actually again means difference only if it is very small. Okay, so why here we call it integral nonlinearity? Because we sum up each step or each stair, right? The first stair here, second stair, third stair, first stair, right? So we integral, we sum them up all the way from the first, I mean the zeros, all the way to this one, for example, right? If I would like to check the difference, the error, here, the red line is idea. And what is the real result? Actually here, right? And how to get this value, because it is on the top of that, and that is on the top of the others, right? We need to sum it up. 你要把它加起来，加到这边，然后得到差值。This is the reason why we call it integral. So what is differential? Only focus on one step or one stair. Okay, that's it. That is the definition for the other one, differential nonlinearity. 如果是 differential nonlinearity, 我们只看单一个跟理想的差值，单一阶。That's it. Okay. So for most of the definitions, actually, they have roots. They have reasons. Okay. Yeah. Engineers wouldn't like to define anything without any reason. No, without most of the reasons to get the best definition for that. But anyway, I told you already, for such kind of INL, actually, we have not only one definition according to the fit 9. What kind of fit 9 you would like to adopt? It will change the result a little bit. Okay, not so much. But even though the ADC is ideal, you still have nonlinearity error. It doesn't make too much sense. I'm ideal, but I have error. It doesn't make any sense, right? Usually people will think, oh, if that is ideal, it means no error, the performance is perfect. So yeah, we can try to redefine such kind of INL, hopefully. All right? Yeah, so what is the other definition can help us get rid of such kind of difficulty? Even though it is ideal, it still has some error. It doesn't make any sense, right? So this is another definition. We focus on breakpoints. You can see, yeah, for example, this is the ideal one. All right? If your result is ideal, then the breakpoints will be uniformly distributed. 均匀分布. Okay? So what is another definition? Oh, never mind. Yeah. This is the measurement result. So we can see, hey, we just focus in the middle. Okay, in the middle. Yeah. We get rid of the first and the last. And we suppose if it is ideal, then the other breakpoints inside should be uniformly distributed. Okay, that's it. All right? So this is the ideal case, and that is the real case. So what is the error? The difference. You can see that is the first, that is the second, that is the third, right? So the difference between the measured one, I mean the measured breakpoints and the ideal breakpoint. The difference is the definition for INL. Anyway, anyhow, you can still see the difference between INL and DNL. For INL, for example, how about this one? Oh, it is summation of the first and the second, and finally, my own. You need to sum them up to get the definition for integral. Okay? Okay? So, what is INL? The measurement, the case measurement result minus the perfect, the ideal case result. That is the integral definition. Okay, but anyway, we focus on the maximum. That's it. That is definition for INL. And how about DNL? Because I told you already, for each one, what is the difference between U and the ideal value? What is the ideal value for each step? LSB, right? So DNL is even easier to understand here. This is the real case, right? So what is the difference between U and the ideal value? Oh, ideal value, 1 LSB, right? That's it. That is the definition for differential. Differential means difference. Okay, that's it. Yeah. Oh, I need to remind you that for such kind of definition, we forget about the first and the last. Okay, we only focus the breakpoints in between, all right, in the middle. So you can see only such kind of, because we have n, it means 2 to n's power, right? We have so many segments. So how many breakpoints you need? Minus than 1, right? If you have 2 segments, then you need only 1 breakpoint to cut 1 into 2. That's it. To cut 1 into 3, you need 2, right? That's it. So this is the overall breakpoints, but we forget the first and the last. Okay, so you can see this, and big N minus 3, all right? Anyway, if the ADC or deck is perfect, then you can see, no difference between the measurement and the ideal value. Because I'm perfect. So with such kind of definition, congratulations. If the data converter is perfect, I promise you, no error. Okay, that is an even better idea for the definition of INL. Okay, yeah, anyway, we still get the maximum one. Yeah, for ideal ADC, INL is 0. Wow, that is really, really important. Yeah, anyway, never mind what kind of definition you have for ADC or DAC, the most important parameter or specification is INL. That is really, really important. All right, and for such kind of definition, yeah, as I mentioned, the first and the last, actually, by definition, that is 0 because we forget about both ends. Later, you will get better understanding why. Okay, just right now. For measurement, for real measurement, ADC, especially for ADC, okay? Yeah, that is the maximum voltage you can have, minimum voltage you can have. How to test the performance? Oh, usually students, new students, engineers will think, oh, we use the sine wave to fully cover the operation range, right? Is it correct? No. Why? According to noise, you have some, okay, so what does it mean? Many of the data to the maximum or to the minimum, they will be over the range, right? If you over the range here, you over the range there, what is the consequence? You will get a lot of fully ones or fully zeros, right? In ideal, you have only one point with this. The other, for each period, only one maximum and only one minimum, 0, right? But in practice, if you have such kind of full range input, sorry for that, you will get much more than one maximum, much more than one minimum. So what is the consequence? Even though you have such kind of ideal pure sine wave, the spectrum pimple, you will have only one line in the positive and on the other one in the negative. Okay, only we call it line spectrum. But with such kind of blah, 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 yeah, the line will be melted. If you are unlucky, you will, because it is still periodic, right? You will get some kind of harmonics. Oh, it is really harmful for your SNR, especially SINET. Okay? So, for test, for measurement, don't be silly. I mean, don't use such kind of full range input to test your ADC. Nobody does anything like this. Usually, the magnitude needs to be a little bit smaller. A little bit. Okay? But not too small. Why? Because for your SNR, signal to noise ratio, you say, hey, look, I reduced my signal. How about the quantization noise? Exactly the same. What is quantization noise? Oh, you have so many quantization levels, right? If you have your signal here, or you have your signal there, if it is ideal, the quantization error is the same, right? Understand? The same condition here, here, over there. So never mind what range you would like to apply for your input. Sorry, this one is exactly the same in idea. Okay? So if you reduce your input signal, the magnitude of your input signal, the result is your SNR will also be reduced because quantization error is still the same. So we reduce the input signal a little bit, but not too much for measurement. That is, again, the ugly truth. Okay, you need to face. Yeah. Don't try to get the maximum input signal. It doesn't make any sense. It will cause a lot of the other problems. Okay? Since INL is the most important specification for your own design, you will see even the simulation of such kind of INL usually takes a lot of time of you. But before that, you need to resize your transistor, resistors, a lot of parameters to fine-tune, right? You spend a lot of time for that. But even after that, you need to spend even more time to simulate such kind of INL. Wow. Yeah. If the number of bits is large, then it takes a very long time. Not only for simulation, but also for measurement. Later, I will show you, I will tell you how to measure it. Yeah. If you have the real chip, then you can measure it. It is readily measured, right? But again, it dominates the cost. Why? It takes a lot of time. But time is money for IC testing. Okay? And you usually, not always, what is the maximum INL? Usually in the middle of your curve, just like this. You can see the curvature look like that, right? So what is the maximum INL you can expect usually in the middle? That's it. That is the idea. So how to reduce INL? Some of the ADC or DAC, they try to do some kind of calibration, all right, to make this point become ideal, because that is in the middle. So after such kind of calibration, trimming, what is the transfer curve look like? It will look like this. Because you make it become perfect. Originally, it looked like that, right? So you can reduce, with such kind of calibration or trimming, usually you can reduce the angle error by 2, okay? Yeah, 50% off, that's it, okay? Anyhow, so this is the idea, right? In the middle, usually the angle is the largest. Anyway, the major effort in HD design is to improve almost everything to make an acceptable yield. That's it. Okay? Anyway, we can go for the other even more interesting idea about effective number of bits. What does it mean? Oh, you say, hey, I designed an ADC with 12 bits, right, in resolution. But after measurement, oh, sorry for that, you only get 10. That is the real idea for ENUB. ENUB means effective number of bits. Yeah, so for example, hey, look. Somebody designed such kind of ADC. And the other guy said, hey, look, 3-bit, ridiculous. I would like to design an ADC with 5 bits. 5 bits sounds better than 3 bits, right? But if you look at the measurement, this is for 3 bits. It looks like linear, right? And how about such kind of 5 bits? It looks like a curve instead of 9, right? So which one is better for INL? Definitely, this one is much better than that. Okay, so nominally, 名目上, you will say, oh, how many bits you have? The more bits only means the more steps, right? That's it. But the more steps, does it mean the better linearity? Oh, no. These two are very good examples for you, right? Not definitely. Okay? Yeah, so resolution, how many bits? Usually is not a good measurement. That's it. Because you can claim, even though you have the final chip, right? After bonding plot, oh, you have 2 or 3 bits left. Then you can claim, oh, look, from the beginning you have 12 bits, right? But you have 3 more bits for nothing. Then you can cheat your consumer. Ah, look, congratulations. I offer you 3 bits for free. Okay, but what they can get from such kind of 3 bits? Nothing, right? So that is the nominal value. You either have 12 bits or in addition to 3 nonsense bits, you can claim, oh, totally I have 15 bits. But after buying the such kind of the so-called 15 bits ADC after measurement, he or she will say, wow, so bad. Not only 12, no, even much less than 12. It only gets 10 or even less, right? Oh, this is the huge difference. So don't believe in the name. Ideally, how much bit the ADC has, it doesn't make any sense. No. We need to focus on such kind of effective number. After measurement, effectively, how many bits left, right? That's it. So the price is supposed to be decided on this instead of how many bits, I mean the resolution from the beginning. No, after measurement, you can think, oh, how much money I would like to pay for the chip. That is the ideal case. All right. Anyway, you can see the effective number of bits, for example, should be dependent on the error, on the linearity error. The more linearity error, it means it has more nonlinearity, right? And it means the effective number of bits will be reduced. That's it. Okay, so enough usually is the most important parameter for you to decide the value of the ADC, how good the ADC is. All right, but even with such kind of very important parameter, we still have quite many definitions. Okay, for example, this is angle-based ENAB. Okay, if you focus on the knife fitting U, right? Even though the ADC is ideal, what is the error? It should be, right? Got it? Right? So based on such kind of definition, you can do some kind of derivation as you like. I don't care. Okay? I verify it by myself. Yeah, at the expense of my own time. All right? If you would like to check it, yeah, spend. You can pay some time to do it. Okay, that is really easy to derive. Anyway, let's go for the result because we don't have such kind of precious time, American time. So allow me to show you the result to check whether it makes sense or not. All right, look, enough. All right, the number equivalent bits. Yeah, that is definition. All right, so it means here. Oh, so what is the definition? Okay, allow me to show you this. NR, nominal resolution. How many bits you claim? Ideally, but after measurement, nu is what? Nu is the measured INL. And as I told you, if it is ideal from the very beginning, we have this in LSB. Okay, that is the ideal case. So 1/2 log 2 of 1/2, it means what? -1, because, right? So you have -1 here. Oh, congratulations. Minus means plus. Bingo. Bingo. You can claim, every bit is valid. 每一个位元皆属有效, right? Perfect. That is the perfect case. You claim you have 12 bits. After measurement, you get this one. So you still preserve 12 bits. So the result is totally reasonable. Okay? If you are curious again, go back to derive it at your own expense of time. All right? Anyway, with such kind of angle, wow. Look, if after measurement, the result is even smaller, but according to the definition with breakpoints. Okay, after that, after measurement, wow, you only get 1/4. Oh, what does it mean? 1/4 means 2 to minus 2 power, right? The minus 2 power of 2. So after log 2 operation, you get positive 2. Wow, perfect. You get 1 extra bit. Wow. The definition is really interesting and useful. All right? Why? If you would like to design some kind of sigma delta ADC, blah, 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 okay, you need to usually have some kind of deck inside, right? For such kind of sigma delta ADC, people usually claim, the ENAB is more than 20 bits, right? But how about the DAC embedded inside? Usually 1 bit, 2 bit, maximum is 3 bit. Really hard to design. With 3 bits, really, really hard. Usually only 1 bit or 2 bits at the most. Okay, but anyway, wow, it was from the beginning. Even for myself, I was curious because by book, everybody tell you, if you would like to achieve such kind of sigma delta ADC with resolution more than 20 bits, what does it mean? The DAC itself needs to have inherent accuracy better than this. 天生的精度 inherent accuracy needs to be better than this. But I told you already, you have only 1 bit or 2 bit DAC in design. How can you achieve such kind of accuracy? You have only 1 or 2 bits. How can you achieve the inherent accuracy more than 20? It doesn't make any sense, even to myself, right? Here, Professor Geiger showed me this kind of definition. Wow, amazing. I got the point, all right? After years of waiting, finally, I knew, what's the secret inside. So it means what? To get 1 extra bit in ENAP, you need to reduce the error. You need to reduce the error by 2. That's it. Okay? So you can guess. For 2 bits, right? All the way to 20 bits, it means 18 bits in difference, right? So you need to reduce the error by what? At least. Okay? That is the fundamental requirement for your DAC. If you cannot make it, sorry for that. Never mind how hard you try, how complicated the circuit you design, I promise you, you cannot make your final ADC with enough better than 20. No. Okay? And this is the reason why usually it has only 1 DAC, 1 bit DAC in design. Why? Because, after you learn such kind of sigma delta ADC, you will know 1 bit means perfect. Okay, that's it. But nothing is perfect. Okay, I have no more time to explain it. When I teach you such kind of sigma delta ADC, I will let you know why 1 bit DAC can be claimed ideal, perfect. That it has another reason. Okay, not here. Okay. So it's perfect. I like it. I love it. So you can see again, if the error is 1/2, perfect, then your ENAP will be exactly the same as the resolution you claim, 你宣告的. All right? So to increase ENAP, you can reduce nu. That's it. Yeah. This is the table for you to refer. That is the ideal value, right? If you reduce it, ENAP will be increased. Sorry. Reduce it. Okay? But the usual case is you cannot reduce it. It will be increased. For example, if you, after measurement, it is increased by 2, you lose 1 bit. By 4, you lose 2 bits. That's it. That is the fair game. Okay, you need to play the game. The rule is very fair. Yeah. Because if you can reduce it, you get more bits. If you cannot, you lose some bits. That's it. Okay? Yeah, anyway. Never mind what kind of definition you have. Yeah. This is some kind of more complicated derivation, but anyhow. never mind how many bits you, how can I say, what kind of definition you adopt, the absolute error is exactly the same. Yeah, how to, okay, even though our time is so limited, but I would still like to help you a little bit. Okay, with this one. See, I take 5 bits ADC, for example. Oh, the ENAP, because you can see a curve instead of a 9 for such kind of 5 bits, right? Right? So, after measurement, you have only 2 bits for ENAP. You will be curious, you will be, how can I say, furious, you will be very angry. So, you will say, hey, there is one way. For example, for such kind of 5 bits, you can omit the last one. You have, after packaging, from the beginning, you have 5 bits. But after measurement, wow, you have only 2 bits in linearity, right? Effectively. So you can say, hey, I can play a game. Play what kind of game? I omit the last. I have only 4 bits. For the users, even internally, I have 5 bits, but I omit the rest. So I only have such kind of 4 MSB for my users. What is the consequence? Oh, you omit 1 bit. It means what? Ideally, the LSB is amplified by 2, right? Because I lose 1 bit. So the staircase will be enlarged by 2. Originally, you have this one and that one, but I just let them go. Since I enlarge my LSB by 2, it is increased by 2. So after measurement, nu is reduced by 50%, right? Got it? Because the staircase becomes larger. That's it. Okay? So nu is reduced by 2. What does it mean? You get 1 extra bit according to our definition. Right? Here. Oh, in LSB. Because LSB is increased by 2. And this is in LSB. 以 LSB 为单位。LSB 增加2倍，所以你量出来之后，它当然就会变成1/2。Okay, so it is reduced by 2. You get 1 more bit here, but don't forget, from the beginning you have 5. You reduce it to 4. You lose 1 bit here. You get 1 bit there. So you gain nothing. All right, that is the very easy to understand explanation for you. Hopefully, you get the point. Okay, so never mind what kind of trick you play. I warn you, you will get the same result. All right, so you had better still show your customers every bit and let them face the consequence. After measurement, they only get 2. If you cheat them, you get, oh, okay, so what is the consequence? If you omit the LSB, all right, the curve, the curvature is still the same, but since you omit 1 bit, right? What does it mean? The first, yes. The second, no. The first, the 6th. Okay? So 1 out of 2. The total number of stairs or steps will be reduced by 50%. So you only have maybe, for example, 0, the second, the first, the 6th. And how about the odd number? The first, the third, the 5th, all of them will disappear. That's it. Okay? You take 50% of the stairs away. That's it. All right. So if you zoom in, ooh, I have here, I have there. Okay, then no. So you have larger steps. That's it. Okay? Yeah. This is a simple idea to explain what's the consequence. And it still makes the sense. It still makes sense. All right. Never mind what kind of definition you have. To the end, the result will be exactly the same. So don't play trick to your customers. It won't help you to make more money. Okay, if they are smart. Yeah, anyhow. Okay, yeah, anyway. And then DNL, I explained already. We only focus on one step. For each step, for each stair, how much difference from the ideal value? I mean the ideal LSB. So that is the definition for DNL. Yeah. Okay. That is the measurement value. According to breakpoint definition, yeah, the difference between here and there, that is one step or one stair. Okay? So what is difference from the ideal value? That's it. Okay? But again, usually we express INL or DNL in LSB. LSB 为单位. It means you need to divide the absolute value by LSB value. That's it. Okay? And by definition, we choose the maximum. That's it. Okay? Yeah. Anyway, I would like to tell you, DNL and INL, they are not directly proportional to each other. What do I mean? If you have larger DNL, does it mean you have larger INL? No. All right? This is a very important idea. On the contrary, if you have very small DNL, does it mean you have also really small INL? No. Okay? So what is the idea? What is the truth behind such kind of idea? Okay. This is also a very important concept I need to help you to debug your own brain. Okay? DNL and INL, they are not the same. Okay? The larger, no. The smaller, no. Why? Again, if you are good students, you listen to what I explain, you will know the concept much easily than the others. Okay? I told you already. The definition for INL integral means summation. Okay? Summation what? You summation your DNL to become your INL. You sum your DNL to become your INL. Okay? So, yeah. INL, by definition, is the summation of DNL. All right? For example, just look like this, the stairs. If you don't want, if you wouldn't like to take the lifter, the elevator, you walk down or up by the stairs. Yeah. So for the first stairs, if the arrow is minus 0.1, and then the second stair is still smaller than the ideal value, minus 0.2, minus 0.4. So to this step, because the arrow for this one, how to measure INL? I told you already, you need to sum up all those. The first stair, the second stair, the third stair, all the way to here, right? So below you, if each stairs becomes smaller than the ideal value, they all get negative DNL. So the summation will have a big impact on yourself. Okay, that's it. That is the very easy concept. Okay, to break the relationship between INL and DNL. Okay, anyway, why? You can see, even the DNL is small. For example, minus 0.1. How about next? minus 0.1. How about next? Minus 0.2, minus 0.1, minus 0.3. Oh, but you need to sum them up for yourself. If you look back to your juniors, hey, they don't do a good job. They get very bad DNL, right? All of them need to sum up to become your INL, right? So before you, if you get a lot of minus DNL or a lot of positive DNL, you need to be very careful because you need to sum them up to become your INL. So minus 1, minus 1, minus 2, minus 1, minus 3. Wow! For you, you have minus 0.8 for your INL. That's it. So the idea is, before you, if there is a lot of positive DNL or a group of negative DNL, sorry, your INL will be really bad because you need to sum them up. Okay? So, this is the idea. Yeah, if this is perfect, but positive and positive, or even more positive, you will get something like that. Positive DNL, I mean. Finally, you will get very bad INL there. Okay? On the contrary, you will say, hey, look, I'm so sad. My DNL is really bad. For example, the first, right? The second, the fourth. No worries. Why? Because you sum them up to become your INL, right? So minus 0.3, positive 0.4, minus 0.5. Yeah, anyway, if you sum them up, congratulations, you still get very small INL. Got it? Got it? So, what is the worst scenario for DNL? A group of DNL be positive or negative, that is really bad. Okay? If they are random, oh, congratulations, you can reduce your INL. Yeah, so we hate positive, and then negative, positive. We hope we can get, for DNL, oh, positive, negative, positive, negative. Oh, that is really good. To randomize your DNL will become a key to enhance your INL. But again, what is the real situation after measurement? Yeah. After measurement, will you get the first case or the second case? Usually, you get this. According to Murphy's law, the one you hate the most will happen. Usually. Okay? 你越不想看到它越会发生. That is the ugly truth after measurement, I promise you. Usually you will get a lot of positive DNL and a group of negative DNL. So how to enhance your linearity? You need to randomize your DNL. Okay? If you don't do anything, according to systematic mismatch, if I'm positive, usually all my neighbors are positive. Okay? According to systematic mismatch. And this is the reason why we need to have very good circuit design or layout to randomize 随机化 your neighbors. Okay? And this is the reason why, anyway, from the beginning, for example, you have a lot of resistors for your flash ADC. Oh, resistor, right? So, by the notation, 编号 1, 2, and 3, and 4. Okay? Don't be silly. During your layout, oh, the transistor at the resistor here, right? And then, usually, if you are lazy, intuitively you will say, oh, the first, the second, the third, the fourth, okay? Is it good? No. According to systematic mismatch, if I am larger than expectation, all my neighbors are more likely to be also larger than the ideal value. So you will get a lot of positive DNL. All right? So how to randomize it? After layout, don't do any numbering like this. No, it's really bad. Don't have such kind of sequential numbers for your devices. You are really silly. Okay. So what we can do? The first here, the second there, the third here. Okay. The first, the fifth, the sixth. Whoa. Okay, that's it. All right. Then you say, hey, I'm the first. And where is the second? Far away. So if I am positive for DNL, how about the second? Who knows? It is randomized. Okay? Got it? So if you would like to enhance the linearity of your ADC or DAC, one of the major technology is to randomize your layout. Okay? That's it. That's it. Yeah. But nothing is free. You need to pay for it. Why? The first here, the second there. But for you, the first, the second, they need to be connected. Right? So the routing will be really complicated. You need to connect the first to the second, then to the third, then to the fourth. It will take you a lot of effort for such kind of layout. And you need to pay attention not only for the complexity of the layout, but also the parasitics. That is perfect in idea, but for real implementation, sorry for that, you need to face very difficult to implement, and you will get a lot of parasitics. Maybe sometimes the parasitic will kill your performance. All right? So nothing is free, pay for it. So hopefully, even through the definition, explanation, what is angle, what is DNL, you will know your own future. To design a good enough ADC or DAC, it is really hard, especially for high resolution one. If the number of bits is really high, and also you would like to get very good enough, a lot of dirty work to do, okay, dirty jobs to do. Okay. All right, some moments. Monotonicity, 单调性. Okay, 单调非常无聊. What is the definition for monotonicity? Anyway, from input to output, the slope needs to be the same. If you increase your input, your output will also be increased. That's it. If you decrease, the other possibility is you have something like that. You increase your input, but your output code is decreased. It's still okay. That is the definition for monotonicity, 单调性. Okay? That's it. So, if you violate the monotonicity, what will be the consequence? Without the monotonicity, you can see, it is increased. Wow! But after some time, even though you increase your input, the output is decreased. It doesn't make any sense, right? Right? But I need to warn you, for high resolution ADC or DAC, sometimes you will get something like this. Okay? It is really hard to keep your promise for monotonicity for very high resolution data converters. Okay? Yeah. For real design, I will tell you why. Okay? Yeah. And the other definition, especially for ADC, okay, missing code. What does it mean? Some of the output never show up. Okay? You say, hey, look, I have 8 bits, so totally I need to have sorry. And you have 256 codes for output, right? But after measurement, you say, hey, look, why? I never see 200 of the other code. Yeah, that is the definition for missing code. So from the very beginning, people will say that the original definition for missing code. Oh, okay, for no missing code, what does it mean? All the codes will show up after measurement. That's it. So you increase your input from the minimum to the maximum. Oh, you will see all the codes. That's it. That's the definition for no missing code. But something will go wrong. Okay? See? Every code will show up after measurement. But we are still really unhappy because you can see, oh, the smaller input get higher output code than the next. It doesn't make any sense, right? So right now, we change the definition for missing code. Not only all the codes need to show up, but also you need to keep monotonicity. Got it? Got it? So if you have something like this, people will still say, hey, you have missing code. Okay? All right? And this is a very good lesson for all of you. Even for such kind of very simple idea for definition, you need to be very, very careful because wrong definition, not good definition, will get very strange, very odd result. Okay? Yeah. Anyway. Oh, an even more important idea for you is if DNL larger than 1 LSB, I promise you, missing code. Why? Why? Because ideally, DNL should be 0. One step. One ideal step. So if DNL larger than 1 LSB, it means, wow, 2 steps. Right? So, by definition, one of the break point is missed. Got it? You don't have any code for this one. So, how to make sure you don't have any kind of missing code? By definition, ideally, the DNL, for each DNL, it needs to be less than 1 LSB. Okay? If it is larger than 1 LSB, I promise you, missing code happens. Right? Weird things can happen if the definition is no good. Okay? So again, not only all the codes need to show up, but also monotonicity. Okay? Yeah. So how to test your linearity? Oh, piece of cake. You can see, hey, look, I have such kind of sawtooth 锯齿波 sawtooth waveform for your input. Yeah, sometimes we call it a triangular waveform, 三角波, and you ask you like. All right? They can say, hey, if it is ideal, I can increase my input from the minimum to the maximum, then I will know the output. Okay? Or you can show such kind of sawtooth wave or triangular wave periodically. If it is ideal, then not only all the codes will show up, but also you have the same number of counts. Okay, that is the idea. We call it histogram. All right, that is the usual case to test your linearity, your RNL and DNL. All right, so you have such kind of one very slow input, linear input. The linearity of your input should be much better than the device under test. For example, if you have 12-bit ADC to be tested, then the linearity of your input wave needs to be better than 3 to 4 bits. Okay, here. You need to be more linear, more ideal to test the others. Okay, that's it. So you need to be also very careful. How to generate such kind of linear waveform? I promise you, very hard. For 12 bit, you need to have 16 bit in linearity for the 9. Really hard. Really, really hard. Okay? Anyway, anyhow. You can see what is the concept of histogram. We call it such kind of histogram. Okay? We usually apply histogram to get your DNL and INL. But why? Why and how? Again, I'm really proud of myself. Yeah. I sincerely hope I'm a very good teacher. See? Just like, okay, you increase your input from the minimum all the way to the maximum. I mean, ideally. And for each step, if it is perfect, then everybody will be exactly the same, of the same size. But unluckily enough, after fabrication, some steps becomes larger than perfect value. Some become smaller. Okay? Then, if you look at this, if you increase your input all the way from the minimum to the maximum, if I'm larger, I will get more water. Got it? Got it? If I'm smaller, I will get less water. That is the idea for histogram. So after this, then you measure the size of the step is proportional to the water, the number of coats you get. Okay, so ideally you would think, oh, that is some kind of ADC. So here, for 0 and 1 and 2 and 3 and 4. During such kind of water, just like water, spread from the left to the right, from the minimum to the maximum. Because not so fast. Sorry, it needs to be very, how can I say? It needs to be very slow, okay? From the left to the right. So from the beginning, because the input is really small, you will say 0. I mean for the output, for your ADC output, you will get 0, 0, 0, 0. After it passes the boundary, you will get 1, 1, 1, 1, 1, and then pass another boundary, you will get 2, 2, 2, and then 3, 3, 3, 3, 3. Oh, many threes for you. Okay? So, the concept is really simple. How many codes you get for such kind of histogram test? That's it. If the step is wider, then you will get more counts. Got it? That's it. So this is a so-called histogram. And again, here and there, we forget. Similarly, the beginning and the end, we forget all of them. And how about the middle codes? What is the ideal value? If they are of the same size, then you will have the first, the second, the third, all of them are the same, right? So the ideal value is the average value. If you are larger than that, then your DNL is positive. You are smaller than that, your DNL is negative. Congratulations, that's it. So the average value, I mean the average count. 你在计算嘛哈？平均的次数 the number of times it happens. Okay? The average count means 1 LSB. Okay? The average value. That's it. Then you can calculate each DNL, right? And after you sum up the DNL, DNL, you will get your INL. That's it. Bingo. So again, what is the requirement? Your input should be very linear. Okay, should be very linear. Never mind with only one or many of the input. Ideally, you will get the same result. Okay, and also another issue to remind you is why we have such kind of why we are forced to forget about the beginning and the end, because from the minimum to the maximum, if you would like to get very good linearity inside, I promise you that is some kind of mission impossible. Okay, because for example, you can charge a current to the capacitor, right? You charge it, right? From the beginning to the end, you will always, if you zoom in, you will always see something like this. Or to the end, you will see something like that. Okay? Saturation, it doesn't make any sense. So this is the reason why, to get good enough linearity for test, we always have something like this. Saturation out of your test range. Bingo. And this is the reason why because you are out of the range, right? You get a lot of zeros here. You get a lot of ones there. That's it. So for histogram, that is the always case instead of usual case. It always looks like this one. Two sharp teeth to both ends. But we forget about those two. That's it. Okay? Yeah. Hopefully you get the idea. So to sum the DNL, you will get the INL. Okay. And again, for DNL, for INL, the definition is the maximum one. Okay. Yeah. This is some kind of indirect measurement, but it's really popular. It's really popular. That is the most important technology for INL test or DNL test. All right. Oh, and the other issue is, see, if you have noise in the input, right? So what is the impact of noise? The input from the, ideally the input is from the minimum to the maximum, right? Without noise. And what is noise? From the beginning, right? It behaves like this way, from the beginning to the end, and then again and again. So, if the water during the spreading process, it doesn't go smoothly from the left to the right. No, it is shaking. So what is the result you can expect? The same, right? If the basket is larger, then you will get more water. The same. If the water is here, but by shaking, according to noise, some of the water will be spread into this one. So, oh, you will get more cold. Oh, no. When the water is here, during vibration, some of the water will be spread into the others, right? So, you get some water from your neighbors, but you spread some water to your neighbors. On average, you gain nothing. All right? That's it. So, I promise you, the measurement noise will be averaged out. Perfect. This is a very good idea, very efficient idea, but nothing is perfect. It has some trouble. What kind of trouble? Let's go back here. You won't see any, you won't notice any error like this. Got it? Okay? During measurement, if you are the guy, you watch the result. Again, I told you already, you will get allowed the 0, allowed the 1, allowed the 2, allowed the 3, then allowed the 5. After that, allowed the 4. Sorry for that. For such kind of histogram test, you don't have any way to check the sequence of happening. 1 after 0, 2 after 1. No, you don't have the chance. Why? Really sad. In idea, you will notice it, but according to, okay, this one, the same. Noise. You don't have any chance to check the sequence of the upper codes. Don't expect you will get 0 and 1 and 2 and 3. No, according to noise, especially for high resolution ADC, it is impossible because the noise amplitude is much larger than 1 LSB. Okay, so right now you have 5, next time you have 9, next time you have 1, next time you have 12. Oh, it's really complicated. I promise you, you don't have any chance to check this one. Okay? So how to make sure you don't have anything like this? We have another test called servo, just like server, okay? Servo. So servo test, yeah. In theory, you can figure out something wrong like that. But what is the problem? Very, very slow. Okay, yeah. Servo test, it takes a much longer time than this. Even for this, okay, if you, I don't think we have any kind of luxury equipment on campus to help you do such kind of histogram test. You need to go to CIC, maybe to National Chen University, because CIC has another lab over there for ADC and DEC measurement. Simply because many of the professors in National Chen University, they focus on data converter design, blah, blah, blah. Okay, you need to go there, pay the money to use such kind of luxury equipment. After setting up, if there's nothing wrong, then you need to wait. Yeah, the more bits you need to wait, the longer time you need to wait. Okay, maybe 1 hour, maybe 1 day. After that, you can collect good enough data. That's it. Okay, you can guess. Wow, if you have 16 bits, or even for sigma delta, wow, you have more than 20 bits. 20 bits means what? 2 to 20th power? And also, sigma delta, or delta sigma, as you like, the operation is really slow. It is very slow, and also you have so many codes. I guess you need to maybe wait 1 or 2 days to get good enough histogram. Okay? Yeah, anyway. Anyhow. Hopefully, you get all my knowledge. All right? Okay, we can have a break here. Again, I need to get my coffee. Maybe 10 minutes back.